Hey everyone, welcome to my 5th video on rolling codes. In my first video, I introduced the concept of rolling codes and we looked at Security 1.0 protocol. That was an introductory video, so I glossed over the base 3 encoding and the accumulator encoding, but multiple people have asked if I'd be willing to discuss the actual encoding. In this video, we'll decode a Security 1.0 signal, and then we'll discuss the various elements of a Security 2.0 signal and decode that as well. Let's get started. So this is what the Security 1.0 protocol sounds like. And this is the Security 2.0. In my previous video, we talked about Security 1.0 and all the different fields that the flipper shows. And then we briefly touched on these packets. So in this video, we're going to go ahead and decode a Security 1.0 transmission. You can see down here I have the raw data from a Security 1.0 transmission. This raw data happens 10 times. And then up here I've graphed it as well. So you can see there's this big pause of 59,000 microseconds. And then there's a pulse of tone for 500, silence for 1500, pulse of tone for 500, etc. until we get to here. Then from here to here, we have this negative 58K of silence, and then we have a pulse at 1500 and so on until we get to the end. And again, this signal repeats 10 times. So next we interpret the silence and tone pairs as a digit. And we're going to use a 0 digit is negative 1500 silence, a 1 digit is negative 1000 silence, and a 2 digit is negative 500. And again, it's a base 3 number, so it's digits 0, 1, or 2. And then a big number of gap, we're just going to put an underscore. So that first one, we had this big number, so we put an underscore. And then this we had negative 1500, so we put a 0. And then we have negative 1000. So we're going to put a 1, and then negative 1500, so we're going to put a 0, and then negative 500, so we're going to put a 2, and so on until we get to the end. And then we have that negative 58 and 15, that's that underscore, negative 15 and 5, that's the 0, negative 5 and 15, that's the 2, and so on until we get to that last digit. That's negative 500 and 1500. Okay, now that we have those two packets, we're going to go ahead and take every other digit from that first packet and then every other digit from that second packet and write them all down. And so we'll get that first row gave us a bunch of zeros, and the second row gave us a bunch of zeros, and then it had a 1, 0, 2, 1, 1. So that gives us this. So that's a base 3 number. So we're going to go ahead and take this base 3 number, 1, 0, 2, 1, 1, and convert that into decimal. And so base 10, we get 103. We take 103, we convert it into binary, and we get a bunch of zeros and then this 11001111 binary. Then we're going to take those same binary numbers, but this time we're going to write it in reverse. So we get this, and then we take that binary and convert it into hex. And we're at E6000000, and that is our count. So next we need to figure out the fixed value. And the fixed values uses an accumulator, which adds digits from both the rolling and the decoded fixed value. We take each decoded fixed digit, and it's basically n is some value times 3, plus the digit that we are trying to decode, and we subtract the accumulator, and then we do modulo 3. You can make n just big enough so that you don't have to do the modulo 3 math. That's what we'll be doing. And then when we get to the end of this first packet, we clear that accumulator back to 0, and we repeat the same process for the second packet. Okay, so I'm going to take that first packet, and we've copied it down here, and now let's apply the rule. So the accumulator starts out at 0. And we're going to go ahead and add this first digit to it, so 0. And then we're going to say 0 times 3 plus this next digit, which is a 1, minus our accumulator, which is 0. So 1 minus 0 equals 1. And so we're going to say our fixed is 1. And our accumulator was 0, but now we've added 1 to it. So we have a value of 1. Next, we have this 0. So we go ahead and add to our value of 1 a 0. And then we're going to do 2 from here. That's our 2. We subtract our accumulator, which is 1. 2 minus 1 is 1. So we write a 1. And then our accumulator was 1. We added 1 more to it. So now we have 2. Our accumulator is 2. The digit is 0. So now we're at 2. This digit is 2. So 2 minus 2 equals 0. And so our fixed is 1, 1, 0. Our accumulator was 2. We add the 0 that we just got. And now we have 2. And this process repeats until we've gotten to the end of the packet. So to get this value here, we just increment it enough that this ends up being a positive value. So if we did 3 times 3 plus 0, that would be 9. Minus 10 is negative 1. So that's why I incremented it to 4. And we got 4 times 3, which is 12. Minus 10, and we got a positive 2. That's how we got that last digit. So at this point, we're at the end of our first packet. So we set our accumulator to 0 and we do it again. Okay, so now we're on packet 2. So copy packet 2 down here. Remember that we set accumulator back to 0 because we're at the next packet. And our first digit was a 0. So our accumulator is 0. 0 times 3 plus our 2 minus our accumulator equals 2. So we write down a 2. I've just put an underscore so we can tell the first packet versus the second. So 2, 0 plus 2 is 2. Our accumulator is now 2. Digit was 0. And so now we're at 1 times 3 plus our 1 minus our accumulator equals 3 plus 1 is 4 minus 2 is 2. So we write that. And our accumulator was 2 and we've added a 2. So now we're at 4. And we continue till we get to the end. So now we take that huge fixed number, which is in base 3. We convert it into decimal, which is base 10. And then we can convert it into hex. And that is our hop or roll code. So if we look at that and you see that that's your hop roll and this is your count, and when we combine those, we have the full key. And then we already talked about it in the other video, but just for completeness, if you take that hop key and you divide it by 27 decimal, you'll get 3B0C3D4, which is that serial number. And if you do the modulo operation instead on that, you'll get 17 decimal, which when you convert into base 3 is 122. And 122 is for ID 1 or ID 0, and 2 is for button right. And the last thing to look at is if we take that hop roll and then the count and we put spaces every other digit, we get the key that we would put in the sub file to be able to generate the Security 1.0 signal. So that's how you could go from a raw signal all the way to a Security 1.0 sub file. Next, let's look at Security 2.0. So Security 2.0 has a key that spans 2 fields, PK1 and PK2. And we take that key and we do all the decryption, which we'll talk about in a moment. And we're able to extract a serial number, the button number, and the count. So here I'm showing the raw data for a Security 2.0 signal. And then down below, we're plotting it. So this is Manchester encoded. And what that means is that you're going to see it's either 250 for the pulse or negative 250 for the silence, or you're going to get a 500 for the silence, negative 500, which is right here. And then here's a positive 500, which is this long tone. These can happen next to each other sometimes. So negative 500, positive 500 is this negative positive. But basically that's how the Manchester encoding signals will look, is you'll either have the 250 length or you might have 2 in a row so you get a 500. In between the big first packet and the second packet is a bunch of silence. And we can see that silence is 68,000 microseconds. And at the end of the signal is another 68,000 microsecond silence, which isn't shown in the graph. And then this signal repeats 10 times. So next we're going to convert our raw data into a bit stream. So when we see a positive 250, we'll write a 1. When we see a negative 250, we'll write a 0. We see a positive 500, we'll write 1, 1. And negative 500, we'll write 0, 0. Negative 68,000 is 272 zeros, so hopefully we won't write all those out. So we have a 250, so we'll put that 1. Negative 250, so we'll put that 0. And we'll continue all the way until we get to this negative 500 here, which we'll write 0, 0. And then we'll get to this negative 500, positive 500, which we'll write 0, 0, and 1, 1. At the end of that line, we have that negative 68,000. So we'll just say 0, 0, 0, 0, 272 zeros. And then we repeat that for that second packet. And there you go. Next, we're going to take our bit stream and we're going to group it into pairs. So we're basically just going to grab 2 digits and copy it down. The next 2 digits, copy it all the way to the end. And then we'll have this 1 here, and then we're going to borrow one of the zeros and copy it at that end. And the same for the second packet. You're going to have the 1 and then the 0 you're going to copy from there. And then we want to take each of these groups and extract the second digit of the pair. So in this case, that's a 0 and a 0. And we'll continue on until we get to here, which is a 1. And so if you see a 1, 0, you're going to write a 0. If you see 0, 1, you're going to write a 1. And that's going to give us these values in binary, and we're going to stop at the end. So that's a 0 and a 0, which are these zeros. Then we're going to take that binary value and convert it into hexadecimal. And at this point, we have the PK1 and the PK2, which were displayed on the flipper 0. Also, you'll notice that PK1 is the Security Plus Packet 1 data, if you just add spaces. And PK2, that 3D29, is the key if you add spaces. So now you know how to go from a RAW file into the Security 2.0 format. So some of you are probably excited that we were able to get the PK1 and PK2 of a Security 2.0. But others of you are like, can you show me the 25 steps required for that serial number and count, how we would decode that information? So yeah, let's go ahead and show you those 25 steps. So the process is similar for the first packet and the second packet. We're going to decode the first packet first. So again, we had that value. I'm going to convert it back into binary so we have it in its long format. And here you can see our packet 1 in binary. Now what we're going to do is start on the right, and every third digit, we're going to grab that and copy down the values down here. So we've got a 0, a 0, a 1, a 0, a 0, a 0, a 1, a 1, a 1, and a 1. We'll take that binary value, putting all those digits together, and we'll convert it to decimal. 964, we'll call that our P2 value. Now when we've already used those digits, we'll go over 1, and we'll do it again. Every third digit, grabbing all 10 digits, convert that binary into decimal. When we got 360, we'll call that P1. And then we'll move over one more digit, grabbing every third. Again, copying them all down, binary, decimal, we'll call that P0. Okay, so I've recorded our P2, P1, and P0 values. So we saw at P0, we ended up here. So next we're going to take those next 4 digits and we're going to copy those down. So we have a 1010, and that's in binary, and we'll convert that into hex, which is 5. And that's our invert method. And then we'll continue on to the next 4 digits, which is 0000. We'll copy those down and convert that to hex, which is 0, and that's our order method. Okay, so next we're going to look at that invert method. So we had a value of 5 hex in our invert method. And to determine what we should do with that method, we have to go look in the code. So we go into this, I think this is a typo, but I believe it's invert. We find our 5 hex, And we can see that we're inverting P0 and we're inverting P2, and they don't mention P1, so we leave P1 alone. Okay, so we're inverting P0 and P2, but not P1. So P0 was this in binary, so we're going to take the ones and make them zeros, the zeros and make them ones, and then we'll convert that into decimal. And this one we're going to leave alone because it's P1. And then P2, we're going to again invert. The ones become zeros, the zeros become ones. And we convert that into decimal, 59. Next, we have our order method, and our order is 0 hex. And so when we look at order decode and we find case 0, we see that P2 equals B, which is P1, and P1 equals C, which is P2. So P2 and P1 will swap places. So we had from before, P0 was 8, P1 was 360, and P2 was 59. And now we're going to swap P1 and P2 and leave P0 alone. So P0 is still 8, but now we have 59 and 360. All right, so this step's probably the most confusing. What we need to do is grab our latest P2 value after all those inverts and reorders. And so that's our P2 value in binary. And we've written out just a helper here of digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then our invert method, remember that was 5. And so we've written that out in binary. And our order method, we've written out in binary, digits 0, 1, 2, and 3 of each of those. So now we're trying to calculate that roll H1. And what we're going to do is we're going to start with, from our order, those last two digits. So 0, 0. In 0, 0, when we convert that into base 3 is a 0. And then we're going to do the first two digits of order, which is 0, 0. And we convert that into base 3, it's also a 0. Next, we're going to do the invert last two digits. So 0, 1. We convert 0, 1 into base 3, it's still a 1. And then we're going to do the first two digits of invert. So 0, 1 is still a 1. Next, we're going to look at our P2, and we're going to look at the last two digits of P2. So this 0, 1 here, or our first two digits of P2, depending on how you're looking at it from left or right. Anyway, the leftmost two digits, we have a 0, 1. So we're going to convert that, and that's going to be a 1. And then we're going to look at the next two digits, and that's a 0, 1, and that's going to be a 1. And then the next two digits is 1, 0, and that's going to be a 2. And then we have 1, 0 again, and that's going to be a 2. And then we have 0, 0, and that's going to be a 0. And so now we've converted the order, invert, and P2 to calculate our roll H1. All right, so hopefully this next step isn't quite as hard. We're going to copy down our P0 and P1 current values. So we had P0 was 8 and P1 was 59 decimal. And to calculate the fixed one, we're going to take that P0 value, which was 8. We'll multiply it by 1024. This is just a constant that the formula for fixed one uses. And then we add our P1 value, which is 59. So 8 times 1024 is 8192 plus 59 gives us 8251 decimal. And that's our fixed one value. So congratulations, we're almost halfway there. We have our roll H1 and our fixed H1. We have to do the exact same process with our PK2 second packet and determine what our roll H2 and fixed H2 values are. I'm going to go a little bit quicker the second time around because we've already discussed all these steps. Okay, so now we take PK2 and we're doing the same process. So we calculate our P2 by pulling down every third bit, and then we do P1, and then we do P0, then we do that invert, and we get a value of 4 for invert, and then we do the order, and we get a value of A in hex. Next, we're going to look up that invert method, which is method 4, and we can see in method 4, we invert P0, P1, and P2. So all three get inverted. And then we'll look up the order method, which is A in hex. And we can see that for A, there's no reordering. Okay, so we copied down the values for P0, P1, and P2. And then we inverted all the bits for all three of them because that was what our invert for method was. And then our order was A, which meant that we kept things in the same order. We didn't swap any of the values. Okay, we're on that roll H2 step, which again is fairly confusing. I've copied down our latest P2 value, which was 65, and I've ordered the digits 0 through 9. I've copied our invert method, which was 4, 0, 1, 0, 0, and our order method, which was 1, 0, 1, 0, and I've written the digits 0, 1, 2, 3. So now we need to do our base 3 conversion again. We're going to start at the leftmost 2 digits for order. So this 1, 0, and 1, 0 in base 3 is a 2. And then we're going to do this 1, 0, and 1, 0 is again a 2. And then we're going to do our invert high ones, which is 0, 1, which is a 1. And then 0, 0, which is a 0. And then we're going to start on the leftmost pairs on our P2. So we have 0, 0, which is a 0, and then 0, 1, which is a 1, and then 0, 0, which is a 0, 0, 0, which is a 0, and 0, 1, which is a 1. And now we have our roll H2. So for our fixed 2, you'll recall we grab P0's value, and we grab P1's value, and we take P0, which was 48, we multiply it by that constant of 1024 always, and then we add P1's value, which is 980. And so that gives us a value of 50,132 in decimal. Okay, now this step is probably the most confusing of all of them. Basically, I've copied down our roll H1 value and our roll H2 value, and I've written down the bits. And so now what we have to do is grab things in little chunks and assemble this roll value. And so what we're going to do is from our H1, we're going to start over here and we have a 0, 0, 1, 1. And now we're going to write that down here in the other direction. So 0, 0, 1, 1. And now we're going to switch over to roll H2. We have 2, 2, 1, 0. And we're going to write that back down in reverse. 2, 2, 1, 0. And then continuing back over to H1, we had 1, 1, 2, 2. We're going to write that down again. Reverse 1, 1, 2, 2. And then we're going to go to H2. And we have 0, 1, 0, 0. We're going to write down 0, 1, 0, 0. And then we have that 0. And then we have that 1. So hopefully you followed that. It's a lot of like flipping things around. That's kind of the obfuscation in this algorithm. And we take this value, remove all the spaces, and go from base 3 into decimal, base 10, and then from decimal into binary. And so there we have our binary value, 1 with a bunch of zeros, and then 1, 0, 1, 0, 0, 1, 1, 1. We're going to write that in reverse all the way. So now we have 1, 1, 1, which was from the end, 0, 0, 1, 0, 1, which is this part, and then a bunch of zeros, and then finally our 1. We take that count from binary, we convert it into hex, and we have the count. Congratulations if you got this far. It's awesome. All right, so we are super close to being done here, folks. So we have fixed 1 was 8251 decimal. I converted that into binary. And then we had fixed 2 was 50,132 decimal, which I converted into binary. For our button, it's that most significant nibble from fixed 1. So those top 4 bits, which is 0010. And we just write down 0010 binary, convert it to decimal. We get a 2, and that is our button. So now we have the button. And then the serial number, we take the remaining bits off of fixed 1, which was 000000111011, and then We continue with all of fixed 2, which is 1100001111010100, and we convert that into hex, and we have our serial number. So congratulations, we got the count, we got the button, and we got the serial number. We successfully decoded a Security 2.0 protocol. So congratulations once again. This is just another view so we can see that we found that count 5E01, which was matched. We found the serial number 3BC3D4, which matched, and we found the button, which was 2. We were able to figure out the PK1, and we were able to figure out the PK2. So we took that raw signal and figured out all the information that the flipper has. Hope you found this video helpful. Please like and subscribe. And if you have any questions, reach out to me in the Discord channel. Thanks a lot.